And we have four distinguished mathematicians here to chat with us. Camillo DeLellis from the Institute for Advanced Study, Ulrike Tillmann from the Newton Institute, Jim Arthur from the University of Toronto, and Ramdorai Sujatha from UBC. You heard from Jim and Sujatha already this morning in math talks, and you'll be hearing from Ulrike and Camillo in a day or two maybe. But besides the math talks, it's good to take advantage of having all these people here together in one place to also discuss something about the nature of our discipline, about the way mathematics is done, about the way mathematics is recognized and how it's communicated. So we wanted to have an informal chat about some of these issues. We're not going to cover everything. We only have an hour. But so it is meant to be an informal discussion. I will raise some points, which I'll ask our panelists to comment on, and then we'll let the discussion flow in a free way. So I wanted to start off our conversation with something which takes its cue from the very beginning of this morning's program when we were speaking about Professor Langlands and his contributions. He is well known for the Langlands program, which is an amazing array of conjectures which describe the interplay between arithmetic and geometry and harmonic analysis and representation theory. In other aspects of mathematics also, there are many important programs or conjectures, collections of conjectures. There's the famous Hilbert's problems. They're not programs, but they're individual problems. But all of these have sort of served to guide the discipline in a certain way, guide attention and focus, and have had tremendous impact on the discipline. On the other hand, we as mathematicians think that unless we're proving theorems, we're not actually doing math. And it's built into even the recognition that we afford. For example, the Fields Medal recognizes theorems, not programs as such. So I thought we would start our conversation with reflecting on these ideas. And I'd like to ask each of you just to share your thoughts first in as you like for a few minutes each. And then we can develop the conversation. Maybe I'll start with Camillo. Let us know how you feel about conjectures versus theorems from your point of view.
Okay, it's bad to be the first one to start, but let me first say that sometimes I feel like in when I hear mathematicians and like especially younger mathematicians speaking about mathematics and prizes, I have the feeling that sometimes the conversation is shifted towards regarding mathematics like a sport in which you have to achieve a certain goal or you have to win something. So luckily it's not a sport. It's not like we're not defined by the fact that we win the World Cup or not, or we win the Olympic medal or not. I'd rather expect that most of the mathematicians actually enter into mathematics because they find it beautiful and fun. But then, maybe secondary aspect, let's say, is that, it's a part of science and we strive for a better understanding of things. And so the ultimate goal is that. And I view prizes as a way to, foster or recognize the work of people, encourage maybe certain developments, but it's not the ultimate goal. So they are an imperfect tool, and they are an imperfect tool for these goals, but the ultimate reason why we do mathematics is something different. Conjectures versus theorem. I think there's a big difference between saying, an isolated conjecture that I might have shot sometimes, in which I'm just saying like, oh, okay, maybe this is true. And something like, the Langlands program, which is kind of a set of conjectures, a set of guiding principles that I know very little about. So maybe I would draw, a parallel with something in areas which are closer to mine, like Hamilton's program for proving the Poincare conjecture and the geometrization conjecture that ultimately was successful. And of course, it was a development of a set of ideas with even before the coming of Tillmann with some success. And that's definitely a different ball game than just conjecture against theorems. I mean, I think a development like that has been central for the field. And you might even think that actually it was more interesting to develop the program to start with all the ramifications, than to actually solve the problem in topology. I mean, at least as an analyst, I would believe that the whole field of geometric flows is way more interesting than just as a tool to solve some geometric conjectures. And I mean, do we recognize this? I would say yes. Maybe not directly at the onset of these ideas. Maybe it takes some time. So maybe something like the Fields Medal is not the optimal tool for the recognition of progress of this kind, because it takes maybe years to or decades to see the fruits. But of course, the people who develop these great programs, they still get the recognition they deserve at the end of the day.
Good, thank you, Ulrike.
So I covered already quite a lot of ground there. No, so I was reflecting on. I completely agree that, of course, in mathematics, probably any scientist or academic is striving to understand rather than to for a prize. On the other hand, sometimes I think, especially for the younger generation, different problems seem to be, well, do I try this or do I try that, or do I try to understand this or do I try to understand that? So when something is called to conjecture, it actually helps to concentrate maybe the mind. And I guess possibly one of the primary examples there is like the Fermat last theorem. I know Andrew Wiles read it when he was a young child, and sort of just having that somehow in his mind was, I think, important ultimately. Of course, the understanding that goes behind it and the proof is, far more important than possibly the conjecture itself. After all, it's just about one equation. But I think it sort of focuses the mind a little bit in that respect. And if I may say one more thing, I think that conjecture is one thing where I guess one expects somebody says something is true, but you already mentioned there's a program, but I think that's possibly even more important and can give us more understanding, right, and more of a framework to work in, and it's not a yes or no answer, which I think is actually also liberating in many cases. So in my own field, there's something called the cobordism hypothesis, and effectively it's really a theorem because Lurie sketched a proof of about 100 pages, but there's so many facets around it. It just gives a complete picture of this whole area, that there's a whole community trying to really understand what it means. So I think that is in many ways more exciting maybe than having a specific conjecture that to go for.
You raised a couple of really interesting points. Firstly, on the Fermat problem, there is the single equation that people might be thinking about, but at the end of the day, it was solved by proving the Taniyama conjecture, which is a structural theorem and of independent interest.
That's what I had tried to say. Of course, it is, but I think just having that, Andrew Wiles read it when he was 12 or something, just having that in the back of my mind, I think was important finally for him to go through. And that, I mean, he had 7 years effectively by himself trying to solve it. It must have been, you have to have a good reason to do that.
Jim, what about you? You're steeped in the Langlands program, and so you're certainly particularly qualified to talk about programs.
I guess what we're discussing here has two aspects, which all three of you have suggested. One is on the actual awarding and meaning of Fields medals, Is there any place for conjectures in the awarding of Fields medals? I just remark in passing that the Fields Medal was originally intended, as probably everybody knows, to have an age limit of 40 to encourage young mathematicians to go on to greater things. I think it's, maybe people will dispute me on this, but I think it's fair also to say that maybe 50 years ago, it was sort of forgotten what these initial constraints were in the Fields Medal, because there were so many strong mathematicians under 40. I'm not saying they don't exist now, they certainly do, but it just seemed that the mathematical world was overwhelmed with strong mathematicians under 40 in the 1960s and 70s, that it sort of took on the aura of a Nobel Prize, which perhaps was not always so good for the mathematical development of the Fields winners. They perhaps sometimes felt they were under extreme pressure to better what they had already done. But in any case, that's an issue about conjectures in the awarding of Fields medals as opposed to theorems. There are obvious difficulties. Conjecture might be wrong, and it's hard to, as Camillo and Ulrike have already said, that there's a difference between conjectures, just sort of one specific conjecture, which may or may not be true, and a much broader program. But anyway, that's an issue for the Fields medals. But then there's also the question, and this is a very broad question, worthy of much discussion. We have to, probably everybody here has an opinion on it, and that is the role in mathematics, the mathematical world in general, about how does it develop and how do we appreciate it, and how do we feel about it, the role of the, how should I say, the tension, that's not really tension, but between conjecture and theorems. And I sort of, it seems to me, you might dispute this, but mathematics is, it seems, as far as I can see, mathematics, in many aspects of mathematics are having increased ties to physics, very beautiful ties often, it would seem. And how do physicists work? Well, I think you could make the case for physicists. There are theoretical physicists and experimental physicists. And I think you could perhaps make the case for conjecture in mathematics is attempting to discover what is true, in the same sense that theoretical physicists attempt to discover what's true about the physical world. It doesn't count in theoretical physics what a theory they might propose until it has been verified by experiment. And so I think you could make the analogy between mathematics and physics in that sense. Conjecture is attempting to discover what's really there. Mathematics, I think the word is Platonists. I think everybody here is a Platonist. They believe, well, maybe I better not say that, but we tend to believe that the mathematics is already there, and we're simply discovering it in the same way physicists are discovering the laws of fundamental physics. And if that's the case, then we feel like we feel as if we've discovered something in a conjecture, but it doesn't count till we have done the analog of proving it experimentally, which is to say, prove it mathematically. So anyway, it seems to me there's all kinds of interesting variations that people would have opinions about.
Okay, so lots of interesting points there. How about you, Sujatha?
Yeah, I am for conjectures, and whenever I hear the word conjecture, I'm reminded of my early years as a graduate student at Tata Institute, and the story of Seshadri proving one case of Serre's conjecture, namely projective modules being free, certain vector bundles being free. And apparently Seshadri was visiting Paris and met Serre, and then Seshadri had proved the case for the polynomial ring with two variables. He thought he had a proof, and but he was afraid to explain it to Serre, because Serre in that article had, he had proved it for polynomial rings in one variable, and for two variables he had said, he had written in French, j'ignore le cas when k is 2. I don't know. I don't know. But Seshadri, with his limited knowledge of French, thought that I ignore the case of k equals 2 because he thought it must be too trivial or too obvious from the case k equals 1. So he gingerly approached Sir and said, I have a proof and I want to know if it's the same as your proof or different. And then Sir said, but I don't have a proof. So I feel, and whenever I teach algebraic number theory, I've noticed that the students are very excited when occasionally you say all these simple statements like Goldbach's conjecture, or what kinds of numbers are Fermat primes and so on, what is known about them. They immediately get the idea of conjectures. And then they say what is known, what is expected. And I find that an easy way to talk to the students rather than just going on about theorems. And then I tell them that the history of algebraic number theory is one of conjectures. What did people believe in the 19th century about, okay, it all started with Euclid's fundamental theorem in arithmetic, and people trying to generalize it for number fields. I mean, is every ideal principle? What kind of rings are these integer rings and so on? And then they somehow warm up to it. So I think conjectures are important. And of course, in my own field, that's the Bird-Swinnerton and Dyer conjecture, which I don't know who said it. I forget who said it. But when Bird-Swinnerton and Dyer made the conjecture, they tested it on those primitive computers of the 60s, and they were brave enough to make a conjecture. And it was some algebraic geometer, I think maybe it was Andre Way, I'm not sure, who said, look at these number theorists. They've been brave enough to make this conjecture, whereas we would be just so hesitant to make some statement like this or a sweeping statement like this. And then again, coming back to Sayre, there was some lecture in which the lecturer said, it's a conjecture of Sayre, and went on to say something. And Sayre immediately got up and said, no, I never made that conjecture. I asked a question. So I think mathematicians are prudent, and I hope it continues to be like that. But I think development in mathematics, and again, BSD is an example. Today we stand at the crossroads where even if you don't prove it, even if you prove that it's wrong, you'll get $1 million. And look at the mathematics it has created along the way.
It's interesting you talk about the Bird-Swinnerton Dyer conjecture. If you think of one of the Bailenson conjectures, it's even worse than Bird-Swinnerton Dyer. Bird-Swinnerton Dyer is asking about something that happens for an L function at a point where you don't know it's defined.
Yes.
These Bailenson conjectures are asking something about an L function at a point that it's not defined, the order of vanishing to be equal to the rank of a group that's not known to be finitely generated. So these guys are brave. That's true. That's true. Let me, so many ideas here to follow up on, but I want to ask Sujatha, is because you were talking about your interaction with students, and I know you have a lot of interaction with the students of all levels. We heard Camillo and Ulrike and Jim also said about why we do math. We do it not because to get an award but because we find it beautiful and we find it engaging. Do you think that the younger generation understands that, or is that something to be communicated there?
I think we need to communicate it. Again, it's about the students who sort of have an innate adventurous mind and who don't care, how long it takes and so on. So typically when I lecture to large, not lecture, I give talks and interact with large number of school students and also high school, university students, mainly in India and also in Canada. And so when I tell them about, they ask me about, what is known, what is a big prize, is this known, is that known? And I usually try to insert Perelman's story, trying to say that for a mathematician, even after years of frustration, when finally things fall in place, that's a feeling which cannot be explained or which you have to discover on your own when you do these problems and so on. So some students get it. And some students, their reaction is, oh, I always knew mathematicians were crazy. So it's kind of these two extreme reactions. But I get very interesting questions from students. So what is the problem for which you have worked on for the longest time? Or what is a conjecture which which has been open for the longest time? So things of that kind. And it sort of and especially in number theory, we are quite lucky to have lots of statements which can be very simply stated and which have been open for hundreds of years. And when you tell them, oh, they sort of gasp in wonder. But I think we could do a better job of communicating the excitement and the importance, relevance of conjectures.
How about you, Ulrike? What is your experience in?
Yeah, I don't know whether I talk too much about conjectures, but I think expectations or what would be really good to be able to prove, and the excitement that comes out of the that I think is important for them all to get. I wonder actually whether there's something more. It's not just specific conjectures or recognition that might be in a Fields Medal or some other prizes, that it's more closer to home at first, namely a community that they feel, oh, doing this, being able to understand that will be recognized in the smaller community they are working with, whether it's at a conference, starting with the university, maybe there's a research group, but then beyond that at conferences and so on. So building that community, I think, is quite important, and building a community that has a common goal or common questions and direction. I think that will help the students and also to go that way. Of course, some are brilliant and they just go off and have their inert idea of what they want to do, and that's fine as well, of course. But I think for some of them, just having this community and it's important recognition as well.
Camillo, any ideas on this whole business about how do we share with our students and the generation that's coming afterwards, just the pure joy of doing mathematics for its own sake?
So before I do that, for the records, I am not a Platonist.
Really?
At least one person is not.
Really?
A Platonist. Yeah, maybe I'm the only one. But
Well, it's good that we have disagreement on the panel,
I would be curious
we get
actually
to
to
bring the
know
whole
how,
audience. We have a
how
vote-
is
we
the
have a-
majority of
Why don't we have a
Platonists?
vote on it?
Should we vote on this? So can we count how many Platonists we have in how many non-Platonists we have in the audience? Who is not a Platonist?
No.
They're asking for it.
Oh, define what a Platonist is. Okay. So you believe that mathematics already exists and that you're just discovering things which exist. You're not inventing it. That is Platonism. I mean, my understanding.
No,
of
I think
Platonism.
that's what it's supposed to
I mean,
be.
this is
yeah.
like, back from high school philosophy, but.
Yeah.
So who is not a Platonist?
So just to be clear, the,
No.
It actually probably.
That's not the definition.
Yes, that's right. that's
exactly.
Probably theories that people have created that no one else might create. But in some sense, the idea.
You're not a Platonist.
The ideas exist.
So just to be clear, those that are raising their hands, so what you're saying is that math is math invented? Those who raise their hands, is that what you're saying? Math is invented? Okay. And then those who feels that math is discovered?
I would say you invent techniques to discover.
It is.
It's
both.
both.
It depends,
It's both.
It depends on the field.
You
Good.
invent techniques
Okay.
to discover.
It depends on the field too. I think.
So that's a good digression. Now let's get back to the.
I'm a purist against Platonism. It's invented for me.
Yeah, but the question to you was.
Yeah, the question to me is where. So well, I think we have to distinguish between the students who are already interested in math and the broad audience. I don't think we have to explain to the students who are already interested in math that we do it for the beauty or the fun of it. I mean, okay, so one should be free to do mathematics for whichever reason the person has, but I would bet that the vast majority of the students who enter into math, actually, they do it because they have a passion for the thing,
they're good at it, maybe.
which is transcending the recognition. There might be, people have different level of competitiveness and famously, even in sports, right? I mean, if you, a guy like Federer, you would ask him and he would tell you, I think, that he does tennis because he loves the, the game itself. But then, Agassi wrote a book saying that he actually hates the game and just wants to, win matches, as far as I understood. So even there is disagreement, but by and large, I would imagine this is my expectation, most of the students who enter into math, actually, they have a passion for it. Now, whether we are actually communicating to the broader audience that we do it for the passion of it, and we're like, doing a good job over there, that I don't know. Do we want to do that besides, like, people could actually stop funding us if we just tell them that we do it for fun?
No, I guess.
I mean, if we tell them we're doing for fun and not because of the fancy applications that we might get, I'm not sure what is going to happen.
I'm more concerned about the mathematical community. So there's another issue that, as you're saying, about how you communicate to outside of our community. Yeah. But the people who are already interested in math, there's nothing to communicate to them. But those who are just at the infancy of their exploration, who are looking for trying to figure things out, is there a need to guide them, and how would you do it?
Okay, let me put it this way. According to my experience, at least, I wouldn't imagine why a PhD student of mine would actually, do a PhD thesis with me, if not because they love the subject. Mm-hmm. I mean, like, you wouldn't choose such an ugly advisor otherwise. So I'm pretty sure of the statistics about the people I know. By and large, of course, I don't have a crystal ball, and, one should ask. But I would imagine that we don't have to explain them. I think, the younger generations, they're already doing math because they're passionate about it.
Yeah. Jim, what is your thoughts on that?
I think there's much to be said on both sides. I think we have to also, we have to keep in mind that it's pretty tough for mathematicians who are graduate students or postdocs or untenured. Simply because many more good students of mathematics have joined us from China, say, and many other countries, and it is very difficult. I think the number of jobs has not increased proportionately, and certainly the number of places in recognized journals has not increased. I guess journals, there have been more journals, but it just seems to me that it's much more difficult for a very good student or postdoc to get a paper published in a recognized journal. So we have to encourage everybody to, perhaps as motivation, continued motivation, to think of the beauty of mathematics. But it is also pretty, I would say, pretty brutal for young mathematicians who are making their way, trying to make their way in the field. And that's something we have to somehow also keep in mind.
So Jim, I'm getting from you a balanced point of view on both topics that we've discussed so far. Firstly, on the question of conjecture versus theorem, you see, we need both. And on the question of communicating to students or to others why we're doing mathematics. Again, you need to be practical on the one hand. On the other hand, you have to understand the beauty and the creativity that's involved in doing that. That's
well, I just think you of course, I think understanding the beauty is what's behind it all, and we should all do our best to communicate that to students. But we do all just with the understanding that they have a pretty tough road often.
Okay, could I ask one more probe on one more aspect of this conjectures versus theorems or programs versus theorems? Could a program or even a conjecture actually lead us in a wrong direction? Could it stifle certain developments, or could something become conventional wisdom and thereby delay actually the kind of disruptive thinking that would be needed to prove a big conjecture? Any ideas about that?
Yeah, well, again, my experience has largely been with interacting with students. I was lucky to have a guide, Parimala, who was very practical, and if we got carried away, would sort of lead us back. But I have had students who didn't want to prove anything else less than the finiteness of Shah, finiteness of the Tate-Shafrevich group. And of course, in India, you have this other extreme of students from various backgrounds for whom the single inspiring figure is Ramanujan. And they are usually shocked when I say Ramanujan got some of his formulas wrong. Or when I tell them that, many of his formulas, people are still trying to prove them. So then they get a little confused and disoriented about mathematics. Oh, but he was so famous. Oh, but he had nobody. He did everything on his own. And somehow then they get confused. He is a famous figure. The world was inspired by him. How could he get things wrong? Or how come some of his things are still not proven after so many years? And so then you need to sit and have a chat with them. Then I find it difficult to communicate what mathematics is really about. But then there are others who get it and who know that Ramanujan, the greatness of Ramanujan came from the fact that he was so passionate. And again, in this connection, I have an interesting story to say. A few years back, the London Mathematical Society organized a centenary when he was admitted as a fellow. And they had various people talking about Ramanujan's influence in various areas. And then all the people from the West, at one point or another, touched about his tragic life, quote unquote, tragic life. And I happen to share very close relation to Ramanujan in a sense. My grandmother and Ramanujan's mother, we shared the same ancestral temple in South India. And I grew up hearing stories about my grandmother talking about this famous mathematician. And when I finished high school, not high school, well, pre-university, it's called in India. And I decided I wanted to do mathematics. And that was the time when getting into professional colleges was very important in India. And people who did well automatically went to do engineering or medicine. So they tried to tell my father that, your daughter is making a mistake. With this kind of marks, you can walk into any professional college. She shouldn't be doing mathematics. But my father said, no, she will do what she wants to do. And in that community, they all knew his tragic story. They all knew that his wife had a terrible life after he died and so on. They could have easily told me, oh, there was this great guy who achieved so much, but what happened to him? He died in penury. But they chose to remember his passion. They only remembered that nothing mattered to him except doing mathematics, even in the most difficult circumstances. And they tried to encourage me despite knowing that background. So I see this as a contrast between the way cultures approach mathematics. So some students in India get that. They remember that passion of Ramanujan, and of course, which has been amplified by Kanigal's book and so on. So it's interesting. I think there's also a cultural component in this somehow.
Ulrike, thoughts on that?
I think that's a very nice answer. I was going to take your question slightly more literal. Michael Weiss, had this idea that Poincaré classes in the smooth and the topological case should, be the same, and in particular vanish after a certain degree, etc. Anyway, he had this idea and worked on it for 20 years, and then suddenly he had to change it and was able to prove exactly the opposite. And indeed, it's amazingly how much his initial idea, and I think it was shared by a large number of people who knew about these sort of things, actually failed. But having had this sort of wrong idea or wrong conjecture held him up probably for quite a few years, and just snapping like that. When you then try to prove the other way around, the opposite, it's quite an important thing, and something to keep in mind. I think there have also been sort of wrong assumptions in other directions, which really help hold up the community, and then suddenly, when you see, try to do the opposite, it actually falls into place. I guess they're not necessarily called big conjectures, but these are.
There's a moving description by Wiles, of how the story of how he had an original argument. There was a gap in it, and then he found the right argument. But I'm sure all of you know that he didn't fix that gap. And in fact, it's quite emotional the way he wrote about it, that in trying to fix it, he realized that the thing that was holding him back on that was actually exactly what he needed for another approach that he had earlier abandoned. So the push to try to create this Euler system, it was wrong. But it took a while for him to figure that out, and then realize that an earlier method that he had. So it's hard to say. It does seem to be true that sometimes a program or a conjecture or an expectation can actually hold us back. Jim, in Langland's program, Langland's conjectures have undergone change. Right? Some of them were not right as exactly they stated, but the system as a whole was organic enough to sort of modify them and correct them. Do you want to say something about that?
The misstatements were actually fairly minor. All of Langland's program, much of it, as it survives today, was written up, as we mentioned at lunch, much of it was written up in a 1969 preprint of 50 pages at a conference in honor of Solomon Bachner. He doesn't call, functoriality hadn't been invented, the term had not been invented. And as somebody, was it you, Sujatha, that said, or somebody said, he has a bunch of thoughts that he does not want to call conjectures. He just calls them questions. Who was it that mentioned that in the talk?
With respect to Sayre.
With respect to Sayre. So there are 7 questions, and there's some inaccuracies simply because the theory hadn't been developed enough. But by and large, they're strikingly accurate. And most of his other, as far as I can think, of his later conjectures that turned out to be very close to correct, I guess I would say. But I mean, in general, it seems to me from what people have said, and that a conjecture that is badly wrong, I think, gets discovered pretty quickly. People work on trying to, if they're working to try to prove the conjecture or to try to figure out consequences of the conjecture, I think if the conjecture is very poorly put together, they find that out pretty quickly. On the other hand, you could have a conjecture that's more or less right and just has needs some adjustments on minor points, and that gets discovered as well. And the third thing is where a conjecture is wrong, but it takes many years to discover that it's wrong. And it seems like there's 3 possibilities for a wrong conjecture, but that's good too, because it stimulates, if it's wrong, period, and but a very interesting conjecture, it means that people attempting to understand its implications, even though it didn't work out, have learned a great deal about the field. So I think that there's, on all 3 cases, they're valuable.
So there is such a thing as good mistakes too.
Yes.
Camillo, your thoughts on this? Can a program or a conjecture
Yeah,
actually stifle developments or delay development?
It's a human enterprise. So I have a hard time believing that sometimes we're not taking a wrong path. I don't think that the wrong conjecture actually is necessarily bad, because it might lead to a lot of discoveries, even though the statement is wrong. I would be more afraid of something which is not as important as we believe, and nonetheless, thousands of people maybe are studying it. That is a distinct possibility, which is more concerning to me. And I was trying to, while we were having the discussion, I was trying to think about examples of that. I mean, I can't think about one, and maybe even if I can think about one, I don't know if I'm going to say, historically or even right now, we're working at this problem, but I think it's irrelevant. But it's a distinct possibility. I don't see why it should be excluded. And well, it's a human enterprise, so sometimes you just go into the wrong direction. I think that is certainly possible. Well, I mean, of course, if ultimately the reason why we do mathematics is that we find it fun, you might have fun even trying to do the wrong thing. or an unimportant thing.
How do we decide something is important?
Societal, I think, just because we're humans.
So collectively over time.
Yeah, I mean, of course, I think each of us has some opinions, especially the most opinionated among us, right? I mean, about why they're doing something or why they're not doing something else, but we don't live in a bubble. So if you ask me, I think at the end of the day, it's very much societal. Is that correct English?
Yeah.
Did I just
Yeah,
invent
yeah,
it?
no,
Yeah,
that's
okay.
good.
So it's not my mother tongue, obviously. So
Okay, so we've got about 15 minutes left. Let me change the topic just a little bit and talk a little bit about collaboration. Traditionally, mathematics used to be a very solitary kind of profession. You write papers, most papers are single author. Occasionally you get two authors. Nowadays, things are changing. You get multi-author papers. You even have things like polymath, with a large number of authors. How do you share with me your thoughts on this change in the way we do mathematics, especially when it comes to saying who do we attribute a theorem to? How do we allocate credit in such cases of collaboration? Any thoughts?
I think it's just like Camillo said, it's the nature of the enterprise. So much has happened. And it's easier to work collaboratively now rather than just plod on your own, even though we have Google, even though it can fetch us all the papers, but just having to read and absorb the enormity towards reaching the goal and understanding what the problem is and understanding who has proved what is relevant to this question and so on. I think it's more efficient to do it collaboratively, unless we have ChatGPT helping us in the future. And one thing, I mean, the first time I learned that in chemistry or in biology or in physics, the authors, if it was a group, then there was weight associated to the names and it was not alphabetical. It came as a bit of a shock to me. Because again, I was maybe born and brought up in mathematics in a different time and era. But it was stressed that it was the exchange of ideas. And like I mentioned earlier, in Tata Institute, we were taught to acknowledge a paper that inspired us, even if we hadn't met the author of the paper. And whereas times have changed. And but this has been one aspect of mathematics that always fascinated me. And also large numbers of people in society, especially in countries like India, their reaction always is, when you tell them, when they ask you what a typical day is like, and then you just say you need a quiet place, you need a pen and pencil, and you need to think, then they immediately contrast it with physical experiments. Oh, but the Large Hadron Collider took so many $1 million to build and so on. And somehow they contrast and compare, So I think we work better collectively. That's my honest feeling. And like I said, the way it has developed, it's also more efficient to collaborate. But I would still think that as a community, it's good that we keep this alphabetical order. And maybe within the paper, we can acknowledge this idea came from this, things like that. That's my opinion.
I think it's a very good idea to keep the alphabetical order in many sense. In my personal
Science, the last name counts. So I'm all right.
So Jim, any other reflections besides that on the nature of collaboration?
Perhaps not a good person to ask. I just through circumstance, I guess I have not had many joint papers. Not that I have any. Not one joint papers, but I maybe ask others.
Thoughts?
Well, I think mathematics is quite collaborative, and I think the younger generation, really does enjoy it. And I think maybe there something has also changed in the sense that being proud of one's own work doesn't necessarily just mean I have achieved this and I want to put it down, but we achieved it in a group and bring the group forward or the collaboration forward. So I think there's also a bit of a shift there. I think that one sees through generations. partly because it's in common maybe, but also, some of the attitudes I think of the members has changed in that direction. And I think what our problem often is, I mean, it's fantastic to collaborate and put all names down and all equal. I think that's it's great. Why not? And then it's when it comes to jobs, you can only give it to one person. And I think that's where the real problem comes, where we do want to actually understand the different contributions to a collaboration. But maybe that can be done also different ways than just like counting 8%.
This is exactly the point, that there seems to be a clash between some practical considerations. There's the whole business of competitive marketplace, people trying to get jobs and so on. And then there's the fundamental humanistic nature of our enterprise, which is, I agree with you, it's very collaborative. It's a lot more enjoyable to work together, even whether we actually publish together or not. It's a lot more enjoyable to talk to each other about what we're doing, get encouragement from each other. So there is an issue, I think, that sooner or later we're going to have to grapple with these things that are pulling us in the opposite directions. And actually, I should let Camillo also weigh in on this whole question of collaboration.
Yeah, I think we are already grappling with it. We are already grappling with it. I mean, there's been an evolution since like, I don't know, 60, 70 years probably. So collaboration was, as you were saying, single author papers were much more common than they are now. And large numbers of collaborators were almost inexistent, right? Decades ago. And now we have more of those examples. Well, it's the way if it's a societal enterprise, that's the way society is going, and society is also adjusting to it in some way. And I can certainly think of examples in the past in which you could already see this trend even like 40, 50 years ago. So, coming, for instance, to prizes, people actually getting at least as a portion of the motivation for the prize for some collaborative works, and they got the prize and their collaborators didn't get the prize. So there was at a certain point a decision that it was appropriate to give the prize to that person and not to the other one. And it's the same, I think, for hiring. And
you're saying that even
we're probably making mistakes as humans in this, but I would say by and large, when I actually see at my experience, it averages out. I think we still have a pretty fair evaluation system in our subject. Much more than in many other subjects that I know of. I mean, I wouldn't dare to say that we are the fairest in academia, but yeah, heck, I mean, let me say it actually. I actually believe that.
I like this. Yes.
I once was in a dinner of humanists, and I said that, and I was just completely destroyed. But, I nonetheless believe it's still correct.
So you're saying that even when there is collaboration, we're already learning to distinguish between the contributions of individuals in some form, perfectly or imperfectly, but we're already grappling with it.
We're probably doing a lot of injustice there, but yeah, I mean, we're human beings living actually in the actual world. A certain amount of injustice seems almost unavoidable.
Let me now take this a variation of this whole business of collaboration. Mathematics is becoming so complicated that sometimes there are theorems that no one person is capable of understanding the entire proof. I mean, for example, for a while, this was the case with the classification of finite simple groups, although David Mumford, I think, is going to give a talk in a couple of days where he says, now it's all checked totally. So how do we deal with this? Now, this is not collaboration in physical space, but in time. I depend on the works of other people that came before me, other people that I never met or never interacted with. And it's just too voluminous for anyone to check. And yet we accept certain things as true. How do you see that affecting our work?
So this is again another aspect that draws mixed responses from students and people I interact with. And especially if it's a mixed student, students are working also in physics or who've had exposure to physics research and so on. For them, anything that's more than 1 year old is already old. And when I tell them that we still use ideas going back to millennia and that mathematics has a longest shelf life, some of the students like it actually, and they appreciate it. But coming to this question of what is wrong, what is right, it's true. And the more complicated it gets, the layers of complexity, there is this added question of how much we are using is right. To a certain extent, I believe that there was this self-correcting mode. People would discover mistakes. But I also noticed that in journals, increasingly the errata, there's fewer and fewer errata. So what is that errata? When somebody finds a mistake, people earlier used to conscientiously publish, even if it was typos. I've looked at papers where people published errata saying, you know, this should be that, this spelling should be that, that should have been Q instead of P, whereas any reader could have probably figured those out. But I guess people were conscientious and wanted to put that as well in print. But now I know there are cases where there are papers with wrong results, but I don't see errata for years. So then I have to tell my students, be careful, you know, do check and so on. So somewhere, I don't know, lean machine learning, machine proofs might help, but I see a red flag there.
Jim?
So is that true that Mumford is going to talk on chat?
He's going to talk about
AI,
implications of AI on math. And one of the things he says in the talk, I think he's going to say, is that some things that were hard to check before have now been checked. He didn't say in the slide, so, but I suspect at least partially by AI. Yeah.
AI or computers?
Well, I mean, there's machine learning, so the proof verification,
Okay,
which is making,
that's different.
but
That's different.
which
That's not
makes
AI.
mistakes as humans.
Yes.
So
It could well. That's another issue. Yeah.
No, but it could possibly also pick up some mistakes which humans can then realize is a mistake. You know?
I mean, actually, even just, you know, genuine programming is still programmed by humans, and there might be mistakes over there too. I mean, even though
Right. So
the machine checks everything. I mean, like
now,
we experience this every time with our computers, right?
Now you're in the situation that Jim was describing about experimental physicists, because if we do, and we don't, but if we were to write independent code, and we're all getting the same result, then that's what gives credibility to the conclusion.
But that's, I think, pretty much what is happening in mathematics too, right? I mean, I don't know how you guys read papers, but it's not like I'm going line by line, right? I mean, I'm just essentially checking, like, yeah, I see the statement of dilemma and I get an idea why that one is true. Then maybe I, you know, compare my proof to the other proof. So in some sense, at least when I mean, this might be very personal, but when I actually check the paper, that is what I'm doing. Like, writing the code myself in some way in my mind, and then I contrast with that.
Right. So I was talking about these massive proofs, massive arguments that it does require a machine to verify. Okay, so we just have a few minutes left. I think maybe we'll just go around and anything you want to add or sum up to our discussion, maybe Sujatha?
Well, I just hope and pray that we are still fortunate enough to not need huge funding to carry our endeavor forward.
So I don't say that too loudly. There is somebody from NSF there. No, we need a lot of funding.
Well, there's also the question for AI, which we didn't talk about, and I know very little about the subject, but might AI be capable of actually finding new theorems, possibly even conjectures? And what do we do then? Are we going to appreciate the beauty of conjectures that have been discovered by AI, even if they're very important conjectures? We have to think about that, I think. And there's also, say, AI composing music. Beethoven, you know, the music that could be written by Beethoven. What do we think of that? Are we going to take the same pleasure in it? Well, anyway, that's getting a little far afield.
But on the point of conjectures, there is something called the Ramanujan machine. It's a piece of AI. And what it does is it spits out conjectures. Some of them have been proved, but they could be wrong too. We don't know. Maybe it just spits out conjectures.
Well, they're probably boring.
Well, some of them look pretty intriguing. So it's in a situation where we don't know, just don't know, but the thing exists. Yeah. Ulrike?
I guess I'm just thinking of what you said. I mean, then we do already have examples, right, where AI has produced conjectures, which then also have been proven by mathematicians. And given the people involved, I think they have been interesting enough to want to prove them. You know, and one example I know about relations between certain knots. So I think AI can help mathematicians. It can possibly in future also suggest proof directions. You know, it's just always so many different ideas you can try to do. So when I say AI, you know, something like ChatGPT or machine learning can possibly help us in that direction. So maybe that computers become collaborators in that sense. But I think ultimately computers are not going to be passionate about anything. And I think the meaning of and the importance, I think, is something that probably we will still have to decide. And finally, since if NS is listening, then I think it is really important that mathematicians get, in particular, money to do, well, to help themselves and to be able to communicate, because I think the communication between mathematicians and, you know, like sitting here and being able to talk and listen and hearing different subject areas and coming together is a really important thing. And that needs to be significant.
Sure. You know, on this question of whether AI can be passionate or reactive, we use Maple. You know, we use algebraic manipulations on symbolic manipulation. I don't think it's not passionate. It's not creative even, but it helps us. It's a tool, and I think we can never replace the human aspect of this, which is where the love of it, the beauty, the realization of beauty, the sensitivity to beauty is coming from. But these are all tools, and presumably they'll get better as time goes on. But right now they're not capable of proving theorems yet. Yeah.
There's one aspect which I think is important for future and possibly also for the younger generation. I think, you know, training in mathematics is extremely important, especially in this new AI around. It's because, you know, ultimately, as you said, it's the humans who are going to be behind these machines, and they will have to really understand it. And the real thinking still has to be done on particular aspects by humans. So in a way, mathematics should be the first.
Absolutely, yeah. I totally agree with that. Camillo, last words.
Yeah, well, let's hope that we're going to be behind the machines. At least that's what that's what I very much hope. I mean, mathematics produced by machines that you're not able to understand. I'm not sure what's the interest of that for mankind. Might be interesting for the machines, but then, you know, maybe we don't want to go there.
No, I'm not sure the machine has a concept of interesting, but maybe as a final word here.
Well, I mean, like, you know, we're okay. So I don't exclude the possibility that the machines can actually really get sentient and intelligent and, like, you know, feel emotions like us. I don't see a reason why they shouldn't.
So it all depends on what you mean by feeling emotions. What you wanted to say.
Well, what is our feeling of emotions? I mean, our you know, electrical reactions in the brain, as far as I know, right? I mean, of course, if you believe there's something else, okay, at the religious level, that is a different story.
Right.
But when you go to these great structures, ancient structures, the pyramids or the beautiful temples in India, and then you marvel at them saying, oh, how did they do all this before the age of machines? So one day, I think ChatGPT and the computers will marvel at our theorems and say, how did they prove all these things without the age of machines? And I think that is ultimate credit to mathematicians.
Okay, that's a really good note to end on. Thank you
mean
very much.
we will become extinct?
No, we
No,
won't.
Oh,
But I'm
okay,
saying
okay.
ChatGPT will appreciate what we did
They-
without ChatGPT.
They became sentient enough to appreciate what we did. So thank you all for your insights. It's clear we just started the conversation.